Good morning, everybody. It's time for Correlation Part 2. And I have with me here this morning my new teaching assistant for the spring of 2020. This is Ronan. Ronan's going to be available to ask your questions. And in fact, the first person that sends me a question about correlation for Ronan to answer on the Folio site will get 5 bonus points. That way I can see if anybody is actually watching these stinking videos. Now remember, the question's got to be for Ronan, so it doesn't actually have to be about correlation. Okay, thank you, teaching assistant. We'll know that you're ready waiting on the wings. Is there anything that you would like to say to the class this morning about online learning?
Hello.
Are you excited about all this online learning stuff?
Yes.
You are? You don't miss school?
I do not miss school.
All right. Well, thank you, Ronan. We'll know that you're waiting and ready for us. All right, guys, so I'm going to go down in the corner here so we can get started on round 2 of correlation this morning. So in our first segment, we talked about how there are different kinds of correlations. You can take a look at the PowerPoint for differences between Pearson and Spearman and point by serial. And which one am I forgetting? Well, that's really embarrassing. The phi coefficient. So we've got 4 kinds, and we're going to be talking about Pearson and Spearman in our next segment. But when we look at correlations, remember that we're looking at the degree of covariation, how much 2 things go together, and we're getting that correlation coefficient represented by the letter R to help tell us about the degree of relationship. Now, the thing about evaluating relationships is, quick refresh, they go from -1 to 1, so scores beyond that are impossible. We're interested in looking at the sign to figure out if the relationship is positive. It'll have a plus sign or just not have a sign with it. Or a negative relationship, you'll see the minus sign. And we also, when we look at the number that we get, can tell us the degree of strength. So we can see this on a scatter plot. Here's an example of a correlation that is very strong and negative. Here is a correlation that is negative, but not quite as strong. By the way, if you're looking at the red PowerPoints, throw them up in PowerPoint. Don't try to look at them from Folio, where there'll be some gobbledygook, because they're designed to do some interactive stuff. So this is me looking at it in the PowerPoint viewer. Here's a negative relationship that is still strong, but we would be looking at something kind of moderate here. And then if we have the dots going to the upper right, that would show us a positive relationship. So again, we need to know the type, we need to know the strength, and then we need to know about some things after we figure out about effect size that might get us into issues. So last time we finished up with a correlation matrix. We can look at several different correlations all at once in one kind of table. But we need to back up and look at some of the assumptions of correlations about how they work, and then talk about how violating those assumptions can make our interpretations of a correlation value incorrect, even if it looks strong. So, the 3 assumptions of correlations that we want to pay attention to are homoskedasticity, linearity, and normality. Homoskedasticity is about the scatter among the data points. We want it to be kind of constant. We want a nice kind of round oval shape that's not lumpy or bumpy. If you're a mashed potato fan, unless you're a weird one that really likes lumps in your mashed potatoes, I'm just kidding. If you like lumps, I'll still like you anyway. But I don't like big lumps in my mashed potatoes, and I don't want big lumps in my data set either, because then it's going to mess with the statistics that I'm trying to do with them. So if we have a correlation scatter plot, we want a nice cloud of lumps that's going to make a nice pool around the data so that if we wanted to put gravy in the middle, it would hold on to it. Right? That's my metaphor for homoskedasticity. Linearity is about whether each of the variables when they work together, if we get a straight line, if we're looking for a correlation that is linear rather than curvilinear or some other direction. And normality talks to the assumption we've been doing since about week 1 with looking at the distribution of data to figure out if they're normally distributed. Again, normality is about having continuous data. So we're not doing correlations here, although there are other kinds that can, that involve nominal data. We're looking at ordinal, interval, or ratio data, and we want that data to be normally distributed. Okay, nice curve. So we have to be careful when we're interpreting correlations because they're sensitive to outliers. We can only use a correlation R value if we're actually looking at a linear relationship. The correlation coefficient will be sensitive or have problems if we have a restriction of range. If we don't have people that vary a whole lot, that can be problematic. We also might have heterogeneous samples. That'll be shown in the homoskedasticity. And the last thing we have to remember is that correlation does not imply causation. So when you're talking about writing up your correlations for me, please avoid words like proves, causes, affects, makes, determines, or leads to. Those are all words that suggest cause, and we can't get at cause when we just know things are related. Things being related is the first step in determining causality. There's actually 3 steps. Knowing that things are related, knowing that one thing comes before the other, that's called temporal precedence, and then knowing that we've eliminated other confounds or things that could be explaining the relationship as well, sometimes called third variables. So all we're doing here is seeing if things relate. We can't talk about cause, we can't talk about affecting. We're just looking at connections. Now, first then, correlation is sensitive to outliers. So if you have an outlier in your data set, here's a correlation that's small, kind of on the border of maybe not looking like much of a relationship. But if you had something like this for your pattern of relationships, you can see how that outlier up here in the corner, all right, isn't doing the same thing as everybody else. So an outlier is a problem in just a distribution of data. It can also cause problems when we make correlations. If we tried to throw a correlation coefficient on this, it would give us a very strong correlation value. But you're going, wait a minute, I don't see everybody clustering around that line. I see everybody down here and this dude doing his own thing, right? So just like the big kid on a tug of war, we talked about Big Matt when we did distributions in my daughter's class about how he always won the tug of war because he had the most power, because he was the big kid, so he was the outlier pulling things. That outlier can also pull a correlation coefficient towards it and make it inaccurate for the rest of the group. So just because we get a big number, we still want to look at the scatter plot and make sure we've got a nice cloud of dots and that somebody isn't having undue leverage. I still imagine this like that tug-of-war rope, where here's Big Matt pulling the relationship towards him when that isn't really what's going on for everybody else. Right? The second thing is that a correlation coefficient only works for things where we have a linear relationship, where they're moving in the same direction or in opposite directions. This figure here is an example of a curvilinear relationship. If we look at the relationship between these two variables, right, it's positive up to a point, and then it's not, right? It's nice, and then it's not. So these two things do have a relationship, but it's not a straight line, right? This kind of curve also works if we think about the relationship between stress and performance. If you are an athlete, you know that you have to have your head in the big game and care about it, because if you don't, you're going to have a crappy game. But if you're too anxious, you're going to choke. So this kind of curvilinear relationship doesn't work well with a straight correlation coefficient. This is the correlation number that would represent the overall relationship between these two things, but this pattern doesn't show a nice cloud around the data. Again, it's not homoskedastic, it's doing a different pattern. So we would need a different math formula to pick up on this curve, and the correlation coefficients we're learning only do a straight line. All right, this would be a better fit, and that takes a different kind of math formula than we're learning. The third thing that can be problematic for correlation is what's called restriction of range. And this is when there would be, out in the real world, a big span of scores. Again, only works with continuous data. Let's say on the relationship for someone between their score on a math test and their score on an IQ or intelligence test. So in the real world, people are going to vary pretty widely on math. We've seen that with some of our stats tests too, right? People scoring really low and people getting really high. All within the same class. And so if we looked at a relationship between these two things in the big world, we would probably see a pretty strong correlation between those two things. It's not perfect, right? Some people really intelligent, but not so great at math. But for a lot of us, there's a kind of connection. But if in our particular data set, we only had a small group of people and maybe only got people who scored well on both, the relationship just for that group might look really different than it did for the overall group. Okay? So if we have a restricted range of people that are only scoring in a certain section of what's possible, we might get an inaccurate view of what's going on for those two variables. So again, here's the big world. Here's what happens for a small section. So we actually like to have a lot of variation in correlations. Okay. The last thing that we could have that would give us a problem is heterogeneous samples, which means people from different groups. If we had two very different groups in our data set, maybe this is women and this is men or vice versa, when we fit a line for everybody, it's going to show us a correlation, but those samples are kind of throwing that off because we've got two very different groups. So we also hope that we have a group of people represented that's pretty broad and doesn't divide down this unequally. All right, and the last thing to remember, correlation is not causation. So if we know that X and Y are correlated, all that we know is X and Y are correlated. They're related. That doesn't tell us that one causes the other. Because it might be that X causes Y, or Y causes X, or they're both interacting together, or something else is going on that makes them look related. Okay? That would be a third variable. Does something Z or some other factor look like it's impacting both of these things? But we didn't measure that. So when we get a correlation, stick with these are related. All right? If we look, for example, at the rate between ice cream sales and shark attacks, or ice cream sales and murder rates, these things do tend to be correlated. But then you're going, wait a minute, so shark attacks make people want to eat ice cream? Or eating ice cream at the beach brings the sharks in to attack them? No, we're probably looking at people in a beach situation, in a hot situation, and that's going to relate to both of these other factors, which makes it look like they have something to do with each other, but they really don't. You know, it's coming from somewhere else. So again, when we get a correlation value, be skeptical. Only know that they're related, not that we know anything about cause. All right, another example. If we look at the relationship between global temperature and pirates, those tend to go up at the same rate over time, right? As time goes on, we have more pirates and we have higher temperatures. But it's not like the pirates are causing global warming, and it's not like global warming is causing people to become more pirates. It's because our population is growing over time that those things appear to be related. All right, so we're going to finish up here in this section. This picture is not homoscedastic. We've got a cloud of dots that's not a nice oval shape. All right. This one, again, not homoscedastic. We've got an outlier going on. This one's a curvilinear relationship. So this value, even when we calculate it, doesn't help tell us the whole picture. This one has an outlier. So we might want to remove that person from the data set so we get a better picture of what's going on for most people. And this one is an example of heterogeneous samples. We don't have a homoscedastic group again, and that's because it looks like we've got two different kind of clusters of people. So that makes this value a little skeptical as well. All right, we're going to need to wrap up for there. In our next segment, we're going to pick up with talking about Pearson and Spearman correlations, and then we will get you guys figuring out how to calculate them. Thanks for watching. Correlation round 2. Stay tuned for round 3.